On August 20th, 1977, a spacecraft the size of a compact car was attached to the top of a Titan III rocket at Cape Canaveral and launched into the sky. 16 days later, its twin would follow. The twin, Voyager 1, became the more famous. Voyager 1 holds the record for the most distant human-made object in existence. Voyager 1 was the first to cross the heliopause into interstellar space. Voyager 1 carries the image of the pale blue dot. But Voyager 2 is the one that actually did more. Voyager 2 is the only spacecraft in the history of human spaceflight to have visited all 4 of the outer planets: Jupiter, Saturn, Uranus, Neptune. 4 worlds. 2 of them no other spacecraft has ever reached, and no spacecraft is currently planned to reach in the next several decades. Everything we know about Uranus as a world, its magnetic field, its ring structure, its deepest atmospheric dynamics, its moons, the extraordinary cliff on Miranda that is the highest known in the solar system, comes from approximately 6 hours of close observation by a machine launched with 1970s technology that passed it once in 1986 and has been moving away ever since. Everything we know about Neptune as a world, the great dark spot that no longer exists, the winds moving at over 2,000 kilometers per hour making Neptune the site of the fastest winds in the solar system, the geysers of nitrogen erupting from the surface of Triton, a moon almost certainly captured from the outer solar system and headed for eventual destruction, comes from approximately a day and a half of close observation by the same machine 3 years later. There has been no follow-up mission. There will not be one for a very long time. Voyager 2 was our only look. And it is now in interstellar space, carrying a golden record and a power source running down, moving at roughly 15 kilometers per second in the direction of the constellation Telescopium. Tonight we follow it. From the launch pad through 4 planetary systems, through the boundary of the solar system, and into the dark space between the stars. We're going to look at everything it passed, everything it discovered, and what it means that some of those discoveries have never been repeated, and may not be repeated within the lifetimes of anyone who is currently alive. If this is the kind of mission briefing you want more of, subscribe and stay with the crew. Strap in. We begin at the beginning, which is not Jupiter. It is the math that made Jupiter possible. The grand tour of the outer planets was not always inevitable. It was a coincidence of geometry that happens once every 175 years. The outer planets move, not quickly by any human standard, but they move. Jupiter takes 12 years to complete one orbit of the Sun. Saturn takes 29 years, Uranus takes 84 years, Neptune takes 165 years. Because they are all orbiting at different speeds, the specific geometric arrangement of all 4 planets relative to each other changes continuously, and the arrangement that allows a spacecraft to use the gravity of each planet to slingshot to the next occurs only under very specific conditions. A spacecraft traveling from one planet to another does not fly in a straight line. It arcs through space along a trajectory determined by the gravitational well of the Sun and the velocity of launch. A gravity assist maneuver works by approaching a planet at exactly the right angle and the right speed, so that the planet's gravity captures the spacecraft on a hyperbolic trajectory, swings it around and releases it moving faster than it arrived. The spacecraft gains energy from the planet's orbital motion, a tiny amount taken from the planet's momentum and transferred to the spacecraft. Jupiter loses roughly 1 milligram of orbital speed every time it assists a spacecraft. The accounting works. No laws of physics are violated. The planetary alignment that made all 4 gravity assists possible in a single mission existed in the late 1970s. The window opened around 1977 and would close by 1978 for the most efficient trajectories. After that, the next equivalent alignment would not occur until approximately 2153. Gary Flandreau, a graduate student at JPL in 1965, calculated this window. He was not looking for it. He was working on a project to identify trajectories to the outer planets, and noticed, in the course of the calculation, that a multi-planet trajectory was possible if launched in the right window. He published his findings, and the concept eventually became the Voyager program. That one graduate student, with slide rules and early computing tools while doing other work, noticed a geometric window that would close within a decade and would not open again within any reasonable planning horizon. This is worth holding for a moment. The Grand Tour existed because someone noticed it while doing something else. If Flandreau had been given a different assignment, or had looked at the calculation from a different angle, or had simply not noticed, the 1977 window might have passed unused, and 2 entire planets would be known only from telescopic observation for another century and a half. The Voyager program was designed to exploit this window. 2 spacecraft, both launched in 1977, both aimed at Jupiter, but on slightly different trajectories. Voyager 1 was optimized for close approaches to Io and Titan, Jupiter's volcanic moon, and Saturn's large atmospheric moon, at the cost of a trajectory that would swing it out of the ecliptic plane after Saturn. Voyager 2 was optimized for the complete grand tour: Jupiter, Saturn, Uranus, Neptune, the full sequence enabled by the geometric window. Voyager 2 would take longer, following a trajectory that kept it roughly in the plane of the solar system and within reach of each planet's gravity assist in turn. Voyager 1 launched first but was on the faster Jupiter trajectory. Voyager 2 launched 16 days earlier, but would arrive at Jupiter 4 months after its twin. Both were on their way to a system of worlds that had been observed closely only from Earth, and that contained secrets that no one on Earth yet knew they contained. The journey to Jupiter took roughly 18 months. During that time, both spacecraft checked out their instruments, calibrated their sensors, and began returning data about the interplanetary medium between Earth and Jupiter. The data was interesting, but not dramatic. Interplanetary space is thin. The density of solar wind particles decreases with distance from the Sun. The magnetic field weakens. The cosmic ray flux from the galaxy gradually becomes more significant relative to the solar contribution. And then, in the spring of 1979, Jupiter came into view. Not as a point of light, as a disk, as a planet, as a world that was resolving from the blurry telescopic observations of centuries into something you could see detail in. Into something that had specific features, specific structures, specific behaviors that the Earth-based telescopes had hinted at, but never revealed with this clarity. The thing that most people forget about Jupiter, encountering it in this way for the first time, is how large it actually is relative to everything in the solar system. Jupiter's mass is 2.5 times the combined mass of every other planet in the solar system put together. Its diameter is 11 times Earth's. You could fit every other planet inside Jupiter simultaneously with room left over. It is not simply the largest planet. It is a world that makes the rest of the solar system, including the Sun's retinue of rocky inner planets and their large outer companions, look like an afterthought. Its great red spot, a storm that has persisted for at least 350 years of telescopic observation and possibly much longer, is larger than Earth. The storm itself, the swirling anticyclone that generates winds at its boundaries of up to 680 kilometers per hour, is Earth-sized. It dwarfs hurricanes. It dwarfs entire oceans. It has outlasted every human civilization that has ever existed, and will outlast, in all probability, every human civilization that is yet to come. Voyager 2 would cross the entirety of Jupiter's orbital radius in the time it took for a single human being to have a moderately eventful year. It would come closest to Jupiter on July 9th, 1979, at a distance of approximately 570,000 kilometers from Jupiter's cloud tops. That sounds far. It is roughly 1.5 times the distance between Earth and the Moon. By the standards of interplanetary navigation, it is a near miss. What it saw changed planetary science permanently. Before Voyager, there was a short list of places in the solar system known to have active volcanism. That list had one entry: Earth. On March 5th, 1979, 3 months before Voyager 2's closest approach to Jupiter, Voyager 1 passed Io, Jupiter's innermost large moon, at close range. Navigation engineer Linda Morabito was examining a Voyager 1 image of Io and noticed a crescent-shaped plume above the moon's limb that looked wrong. It was too large and too regular to be a mountain, and it was protruding beyond the surface into space. She looked at it for a while, and then told her supervisor. It was an erupting volcano, the first active volcano ever observed anywhere other than Earth. Not a dormant volcano, not a caldera, an actively erupting volcano, throwing material 290 kilometers above the surface of a world 280 million kilometers from Earth. By the time Voyager 2 passed Io on July 9th, 1979, it had confirmed the Voyager 1 discovery and extended it. Io was not merely volcanic. Io was the most volcanically active body in the solar system. Its surface was covered in sulfur and sulfur dioxide in a palette of yellows and oranges and reds and whites that had no precedent in any planetary image ever taken. The surface had almost no impact craters because the volcanic activity resurfaced it so frequently that craters were buried before they could accumulate. Io's surface was younger in terms of how recently it had been laid down than Earth's surface. Perhaps years old in places, perhaps days. The mechanism driving this was tidal heating. Io orbits Jupiter in a resonance with two other large moons, Europa and Ganymede, that continuously perturbs its orbit into a slightly elliptical shape. As Io moves closer to and farther from Jupiter in this elliptical orbit, Jupiter's enormous gravity squeezes and stretches Io. The interior flexes. The flexing generates heat through friction. The heat melts rock. The molten rock erupts. Earth's volcanism is driven by radioactive decay in the planet's interior. Io's volcanism is driven by the gravity of a nearby giant. It is one of the most elegant mechanisms in the solar system, and it produces one of the most extreme environments. A surface temperature that averages well below freezing in most places, but is interrupted by lava lakes that exceed 1,000 degrees Celsius. Europa told a different story. Europa, the second of Jupiter's 4 large Galilean moons, has an icy surface. This was known before Voyager. What was not known was the character of that ice. Voyager's images of Europa showed a surface almost entirely lacking in craters, which indicated either recent resurfacing or a surface young enough to have accumulated very few impacts. The surface was crossed by a network of lines and ridges that suggested the ice had fractured and refrozen multiple times, that the surface was not a static frozen block but a dynamic crust moving on something beneath it. The something beneath it was most likely liquid water. The tidal heating mechanism that made Io volcanic was also acting on Europa, with less intensity but with profound consequences. The interior of Europa, insulated by the ice above, maintained a temperature high enough to keep water liquid beneath the surface. Europa's ice was a shell floating on a global ocean. The ocean of Europa, if it exists as the data from Voyager and subsequent missions strongly suggests, contains more liquid water than all of Earth's oceans combined. It has existed for billions of years. It is in contact with a rocky seafloor. It has a source of energy in the tidal heating mechanism. It may have chemical complexity driven by the material cycling between the surface ice and the deep ocean. The moons of Jupiter that Voyager 2 observed deserve a longer treatment than the brief mentions they typically receive in accounts of the mission, because each one tells a different story about how the solar system forms and evolves diverse worlds from similar starting materials. Ganymede is the largest moon in the solar system, larger than the planet Mercury, with a radius of 2,634 kilometers. It was known before Voyager to be large. What was not known was that it has its own magnetic field, a discovery made not by Voyager, but by the Galileo spacecraft that visited in the 1990s, building on Voyager's foundational characterization. Ganymede's surface shows two distinct types of terrain: ancient dark regions heavily cratered and covering roughly a third of the surface, and younger lighter grooved terrain that formed through tectonic activity at a later point. The contrast between these terrains tells the story of a moon that was geologically active for a period and then quieted. Callisto, the outermost of the 4 Galilean moons and the least internally active, is covered almost entirely with ancient craters. Its surface records billions of years of impact history, without significant erasure by geological activity. It is the most heavily cratered body of its size in the solar system. Where Europa's surface is young and smooth and suggests continuous renewal, and Io's surface is so young that it is essentially unreadable geologically, Callisto is the opposite extreme: a fossil, a record. Together, the 4 Galilean moons span a range from Io, internally active enough to continuously resurface itself with volcanic material and have essentially no geological history visible on its surface, to Callisto, internally dead enough to preserve a nearly complete record of impact cratering over billions of years. Europa and Ganymede fall between these extremes in different ways. The gradient is driven primarily by their distances from Jupiter and the resulting strength of tidal heating. This gradient from the most tidally heated innermost moon to the least tidally heated outermost moon is a controlled experiment. The moons formed from similar material in similar conditions. The primary variable is how much tidal energy Jupiter's gravity deposits in each one. Studying all 4 gives you 4 data points on the same experiment, with the variable being the intensity of tidal heating. It is one of the most elegant natural experiments in planetary science. The ring system that Voyager confirmed around Jupiter was unexpected. Before Voyager, rings were considered a peculiarity of Saturn. Voyager 1 detected faint rings around Jupiter in 1979, and Voyager 2 confirmed and characterized them. The Jovian rings are thin, faint, composed of dark material, and radically different in character from Saturn's rings. They are maintained by material ejected from small moons by micrometeorite impacts. They exist because the small moons exist, and the small moons exist because Jupiter's gravity has captured or held debris in those orbits for billions of years. The ring system was not on the pre-mission checklist as a likely discovery. It was a surprise. It became one of the indicators that planetary systems are more complex and more surprising than models built from terrestrial observations can predict. The expectation that rings were Saturnian peculiarities was abandoned in the 1979 to 1981 period, when Voyager 1 and 2 discovered rings around both Jupiter and Uranus. The magnetosphere of Jupiter is another major area of science that the Voyager missions characterized. Jupiter's magnetic field is roughly 20,000 times stronger than Earth's at the surface. The magnetosphere it creates is enormous, extending millions of kilometers in all directions. The interaction between the magnetosphere and the Galilean moons, particularly Io's volcanic activity, which continuously injects sulfur and oxygen ions into the magnetosphere, creates a system of plasmatory and particle radiation belts that are among the most intense in the solar system. Voyager 2's instruments measured particle radiation levels near Jupiter that would be lethal to an unprotected human within minutes. The radiation environment is the primary engineering challenge for missions that want to operate near Jupiter for extended periods, as Galileo and Juno discovered. The spacecraft electronics must be hardened against radiation damage. The power of Jupiter's radiation environment is something that Voyager characterized sufficiently well to plan subsequent missions around. Voyager 2 confirmed and extended these observations during its Jupiter flyby. It imaged Europa's surface in detail, tracked the dynamics of Io's volcanic plumes, contributed to the characterization of Ganymede and Callisto, and made measurements of Jupiter's magnetic field, radiation belts, and atmospheric dynamics. And then it used Jupiter's gravity to do the thing the mission had been designed around. It accelerated. The Jupiter gravity assist added roughly 8 kilometers per second to Voyager 2's velocity. More importantly, it redirected the spacecraft's trajectory toward a point in space where Saturn would be approximately 2 years later. Not where Saturn was when Voyager 2 was at Jupiter, where Saturn would be, accounting for Saturn's continued orbital motion in the intervening time. The navigation required predicting the position of a planet 2 years in the future, and aiming a spacecraft at that predicted position with enough precision to thread through Saturn's ring system at the right distance from the planet. This calculation was made by people with computers that had less processing power than a modern pocket calculator. The specific mechanics of the gravity assist deserve more careful treatment, because the elegance of what Voyager 2 accomplished is not fully visible without understanding what the gravity assist actually is. A spacecraft traveling through the solar system is subject to the gravitational influence of every massive object in the vicinity. Near Jupiter, Jupiter's gravity dominates. At the distance of Earth, the Sun dominates. The trajectory of the spacecraft is the result of all of these gravitational influences acting simultaneously, and calculating that trajectory accurately requires accounting for the gravitational effects of every significant body along the path. When a spacecraft approaches a planet, the planet's gravity pulls the spacecraft toward it. If the spacecraft has enough velocity, it does not fall into the planet but follows a hyperbolic trajectory, approaching along one branch of the hyperbola, swinging around the planet and departing along the other branch. The spacecraft's speed relative to the planet is the same when it leaves as when it arrived, by conservation of energy in the planet's reference frame. But the planet is moving. It is orbiting the Sun at its own velocity. When you move out of the planet's reference frame and into the Sun's reference frame, the spacecraft's velocity changes. The direction of the change depends on whether the spacecraft passes behind the planet or in front of it, relative to the planet's orbital motion. Behind the planet, the spacecraft gains velocity from the planet's orbital motion. In front, it loses velocity. Voyager 2's trajectory was designed to pass behind each planet in turn, gaining velocity from each planet's orbital motion. Each gravity assist transferred a small amount of the planet's orbital momentum to the spacecraft. The amount taken from any individual planet is negligible, comparable to a mosquito landing on a freight train. But to the spacecraft, each gravity assist represented a significant increase in velocity that would have required an enormous amount of fuel to achieve through rocket propulsion. The alternative to the gravity assist for reaching Neptune is straightforward to calculate and sobering to contemplate. A direct trajectory from Earth to Neptune, with conventional propulsion providing all the velocity needed, would have required so much fuel that the rocket to carry it would have been larger than any rocket ever built. The gravity assist made Neptune reachable with a spacecraft that could be launched by a Titan III rocket, a large but not extraordinary launch vehicle. The navigation required to thread all 4 gravity assists in sequence to arrive at each planet at precisely the right time, angle, and velocity to be redirected toward the next planet involved calculations of extraordinary precision. The planets were not where Voyager 2 was when it aimed at them. They were where they would be when Voyager 2 arrived, months or years later, accounting for their own orbital motion during the transit. The spacecraft had to be aimed at points in empty space where the planets had not yet arrived, and had to arrive at those points at exactly the time the planets did. The accuracy required for the Jupiter gravity assist was sufficient that a targeting error of a fraction of a degree in the initial launch trajectory would have sent Voyager 2 on a path that missed Saturn or arrived at the wrong time. The error margins on the gravity assist sequence were extraordinarily small, and maintaining the trajectory required periodic course correction burns using the spacecraft's onboard thrusters throughout the journey. The JPL navigation team that designed and maintained this trajectory did so over the course of 12 years, from launch through the Neptune encounter. The people who calculated the initial trajectory and the people who made the last course corrections were not all the same people. The mission spanned careers. Some of the original team members retired before Neptune. Some joined the project after Jupiter. The continuity was maintained through institutional knowledge and documentation, and the specific culture of a team that understood what was at stake. The Grand Tour was a human achievement in multiple senses. The physics of the gravity assist, the engineering of the spacecraft, the navigation of the trajectory, and the institutional continuity that kept the mission running for 12 years through changing political and budgetary conditions and the changing composition of the team. All of it working together produced something that the universe made possible for one brief window and that will not be possible again for over a century. They were right. Saturn is farther from the Sun than Jupiter by roughly the same distance that Jupiter is from the Sun in the first place. This statement is worth sitting with. Saturn's orbital radius is approximately twice Jupiter's. Jupiter is already more than 5 times the Earth-Sun distance from the Sun. Saturn is more than 9.5 times. By the time Voyager 2 reached Saturn in August 1981, after almost 4 years of flight from Earth, it was moving through a region of the solar system where sunlight is roughly 1% as intense as it is on Earth, where the temperature of any unheated surface is approximately minus 180 degrees Celsius, where the interplanetary medium is thin enough that collision with a micrometeorite is a genuinely rare event, even over the course of months. Saturn is a gas giant like Jupiter, but distinctly different in character. Its mass is approximately 95 Earth masses compared to Jupiter's 318. Its composition is similar, primarily hydrogen and helium, but its lower density is so extreme that Saturn would float in water if a sufficiently large ocean existed. No other planet in the solar system has a bulk density lower than water. Saturn sits at 0.69 grams per cubic centimeter. Water is 1 gram per cubic centimeter. Saturn is less dense than the ocean. The rings are the thing that no description fully prepares you for when you see the actual images. Galileo first observed the rings in 1610, though he did not understand what he was seeing and described Saturn as a triple planet. Christian Huygens correctly identified them as a ring surrounding the planet in 1655. Since then, the rings have been observed from Earth by centuries of astronomers who gradually understood more about their structure and composition. But the scale of what the Voyager images revealed exceeded what Earth-based observation could predict. The ring system extends from approximately 7,000 kilometers above Saturn's equator out to 80,000 kilometers, a radial span of 73,000 kilometers. Within that span are thousands of individual ringlets, gaps, resonant structures, and density waves driven by the gravitational interactions between the rings and Saturn's many moons. The rings are composed almost entirely of water ice particles, ranging in size from dust grains to house-sized boulders, each orbiting Saturn independently according to Kepler's laws. The thing that cannot be conveyed adequately without the numbers is the thinness. A ring system 73,000 kilometers in radial extent, which is roughly 5 times the diameter of Earth, is in most places only 10 to 100 meters thick. Some regions are 20 meters thick. The ratio of the diameter to the thickness of Saturn's rings is roughly comparable to the ratio of a sheet of paper to its width. A sheet of paper scaled up to match the ring diameter would be a sheet of paper roughly 300 meters wide and half a millimeter thick. Saturn's rings tell a story about the physics of self-organizing systems that is worth dwelling on. Each particle in Saturn's rings follows its own individual orbit around Saturn, subject to Saturn's gravity and the gravitational perturbations of the ring's other particles and Saturn's moons. There is no ring as an object. There is only an enormous collection of individually orbiting particles that happen to be in roughly similar orbits, each one following Kepler's laws, each one influenced slightly by its neighbors. The complex structure of the rings, the thousands of ringlets and gaps and density waves that Voyager resolved, emerges from these individual interactions. The gaps at specific distances from Saturn are maintained by resonances with Saturn's moons. A particle at a distance where it would orbit Saturn exactly twice for every one orbit of Mimas, the innermost major moon, receives a gravitational kick from Mimas at the same point in each orbit. The kicks accumulate and drive the particle out of that orbit. The gap maintained by this resonance is called the Cassini division, visible from Earth through a modest telescope, and it is roughly 4,800 kilometers wide. The Cassini division is not empty. It contains material, but the material is concentrated in thin ringlets rather than forming a continuous sheet, and the density is lower than in the main rings. It is a gap in the relative sense, not in the absolute sense. What Voyager's images revealed was that this kind of resonance structure is not a single feature, but pervades the entire ring system at scales down to the resolution of the cameras. Every moon with an orbit near the rings creates resonance patterns in the ring material. The result is the intricate layered complexity visible in the Voyager images, a structure organized by the same gravitational physics that organizes planetary orbits, operating at radically smaller scales in a disk of ice particles rather than a protoplanetary disk of gas and dust. Saturn's rings may be relatively young. The geological evidence suggests that the ring system as it currently exists may have formed only a few 100 million years ago, in the era of the dinosaurs on Earth. Before that, Saturn's rings may have been much less prominent. After some future event when the ring material is gradually lost to the planet through various processes, Saturn's rings will be much less prominent again. We are seeing Saturn's rings during a cosmically brief period of prominence. This possibility, that Saturn's iconic appearance is a temporary feature of a specific epoch rather than a permanent characteristic, reframes what the ring system means. We think of Saturn as defined by its rings, but Saturn has been Saturn for 4.5 billion years and will continue to be Saturn for billions more. The rings have existed in their current form for perhaps a few 100 million years. We happen to be here during that window. Voyager 2 also added substantially to the census of Saturn's moons. Before the Voyager missions, Saturn was known to have 9 moons. The Voyager flybys discovered 3 additional moons and characterized all of them in varying degrees of detail. The subsequent Cassini mission would bring the total confirmed moon count to over 80, including tiny irregular moons captured from the outer solar system. The diversity of Saturn's moons, from the enormous Triton with its dense nitrogen atmosphere, to the geologically peculiar Iapetus with its two-tone coloration, to the hyperactive Enceladus, to the tiny shepherd moons that orbit within the rings themselves and maintain the ring edges through gravitational herding, represents one of the richest collections of diverse worlds in the solar system. Voyager 2 initiated the scientific characterization of this collection. Cassini completed much of it, and some questions remain open even after Cassini's 13 years in orbit. Voyager 2 passed Saturn on August 26, 1981, at a closest approach of approximately 101,000 kilometers from the cloud tops. This was a deliberately different trajectory from Voyager 1, which had been targeted to fly close to Titan, and in doing so was deflected out of the ecliptic plane, ending the grand tour for that spacecraft. Voyager 2's Saturn encounter was planned to preserve the trajectory toward Uranus, which required a specific geometry of approach and departure that constrained where the spacecraft could pass relative to Saturn and its moons. Even within those constraints, the Saturn encounter produced extraordinary science. Enceladus, a small moon 500 kilometers in diameter, showed evidence of a young surface with very few craters, suggesting active resurfacing. The degree of geological activity implied by the surface age was unexpected for such a small body. Years later, the Cassini mission would reveal that Enceladus had geysers of water vapor erupting from its south pole, a subsurface ocean, and organic chemistry in the plumes that made it one of the most compelling astrobiological targets in the solar system. Voyager 2 saw the first hints of what Cassini would confirm in detail decades later. Mimas, another small moon, showed the impact crater Herschel, which is about 1/3 the diameter of Mimas itself. The crater is so large relative to the body it is on that the impact that created it came close to shattering Mimas entirely. Mimas looks like nothing so much as a specific science fiction space station, which is an observation that has been made many times and needs to be made here because the resemblance is genuinely striking. Tethys, Dione, and Rhea each revealed their own surface complexity, their own mix of ancient cratered terrain and younger, smoother regions indicating partial resurfacing events in the geological past. Titan, which Voyager 1 had observed at closer range but found opaque in visible light due to its thick haze layer, was observed by Voyager 2 at greater distance. The haze remained impenetrable to the cameras. Titan's atmosphere was denser than Earth's at the surface and composed primarily of nitrogen, with methane playing the role that water plays in Earth's atmosphere, cycling through gas and liquid and solid phases, raining onto the surface, pooling in lakes, evaporating and returning to the atmosphere. The scale and scope of this would not be fully understood until Cassini arrived, and the Huygens probe descended through Titan's atmosphere in 2005. Saturn's gravity assist added more velocity to Voyager 2 and redirected it toward a part of the solar system that no spacecraft had ever visited. Not toward a planet anyone was particularly certain about. Not toward a well-characterized world with decades of spacecraft visits to calibrate expectations. Toward Uranus. A world that, in 1981, was known primarily from Earth-based telescopic observations, accumulated over roughly 2 centuries since its discovery. The journey to Uranus would take 4.5 years. The things waiting at Uranus would rewrite what planetary science thought it understood about how planets could be structured. Uranus is rolling, not rotating. Rolling. Every other planet in the solar system rotates with its axis tilted at some angle to the plane of the solar system, but for most planets that tilt is modest. Earth's axial tilt is 23.5 degrees, which gives us our seasons. Mars's is 25 degrees. Jupiter's is only 3 degrees. The gas giants are, for the most part, roughly upright relative to the plane of the ecliptic. Uranus's axial tilt is 98 degrees. This means Uranus is essentially lying on its side, rotating with its poles roughly in the plane of its orbit around the Sun rather than pointing roughly perpendicular to it. The consequence is the most extreme seasonal variation of any planet in the solar system. During Uranian summer, the pole that is tilted toward the Sun receives continuous sunlight for 21 Earth years. During Uranian winter, that same pole receives no direct sunlight for 21 Earth years. The opposite pole experiences the reverse. When Voyager 2 arrived at Uranus on January 24, 1986, the South Pole was pointed almost directly at the Sun. The spacecraft approached essentially from the direction of the South Pole and departed in the direction of the North Pole. This geometry meant that the geometry of the encounter was not like the Jupiter or Saturn flybys, where the spacecraft moved more or less parallel to the planet's equatorial plane. It was approaching one pole and leaving from the other, passing through the Uranian system in a direction roughly aligned with the planet's axis. The geometry constrained what could be observed. The rings and most of the moons were in a plane that, from Voyager 2's approach direction, appeared almost face-on. The science team had to adapt observation strategies designed for equatorial approaches to a polar approach geometry. They succeeded, but the geometry limited the quality of some observations. What Voyager 2 found at Uranus overturned several prior assumptions. The first was the assumption that Uranus was geologically inactive. Before Voyager, Uranus was expected to be a boring world, a featureless blue-green ball with a thin atmosphere. The images returned by Voyager 2 showed the visible disk of Uranus to be essentially featureless in the optical bands, a smooth, pale, blue-green sphere with almost no visible atmospheric structure, no equivalent of Jupiter's Great Red Spot, no visible banding, no dramatic cloud features of any kind. By the standards of dramatic planetary appearance, Uranus was anticlimactic. But the moon Miranda told a completely different story. Miranda is the smallest of Uranus's 5 major moons, about 470 kilometers in diameter. It was discovered telescopically in 1948 and was expected to be an unremarkable small icy body. What Voyager 2 revealed was one of the most geologically bizarre surfaces in the solar system. Miranda has regions of ancient cratered terrain interrupted by dramatically different terrain types that appear to have no gradual transition between them. Chevron-shaped features called coronae, whose origin is still debated. Fault scarps and ridges crossing the surface in patterns inconsistent with simple impact cratering. And Verona Rupes. Verona Rupes is a cliff, the cliff on Miranda. It is the tallest known cliff in the solar system. Its height is estimated at between 5 and 10 kilometers, with 10 kilometers being the more commonly cited figure. For comparison, the height of Mount Everest above sea level is approximately 8.5 kilometers. Verona Rupes drops roughly 10 kilometers, essentially straight down. Miranda's gravity is approximately 0.079 meters per second squared compared to Earth's 9.81. If you fell off Verona Rupes on Miranda, you would fall for approximately 12 minutes before hitting the bottom, and you would be moving at approximately 100 kilometers per hour when you hit. You would not survive, but you would have had 12 minutes to look at the view. The origin of Miranda's geology is genuinely uncertain and remains a topic of research. The leading hypotheses involve some form of tidal heating during an earlier period of Miranda's history, when its orbital resonance with other moons was different from today, or a large impact that shattered Miranda and caused it to reaccrete with the various terrain types reassembled randomly. Neither hypothesis perfectly explains all of the features. This is the specific character of the Uranus data, sufficient to reveal that the system is far stranger than expected, and insufficient to resolve the strangeness. 1 flyby, 1 pass, 6 hours at closest approach. Extraordinary data, but data that was always going to ask more questions than it answered, and whose follow-up questions would require a follow-up mission that has never been funded and launched. The obliquity of Uranus, its extreme axial tilt, deserves a careful treatment, because the consequences of rolling through an orbit on your side are more strange than the number alone suggests. Uranus orbits the Sun roughly every 84 Earth years. With an axial tilt of 98 degrees, the sequence of seasons that results is unlike anything in the solar system. During Uranian northern summer, the North Pole points almost directly at the Sun. The northern hemisphere receives continuous sunlight for roughly 21 Earth years. The southern hemisphere is in continuous darkness for the same period. Then the situation reverses during northern winter. When Voyager 2 arrived in January 1986, the south pole of Uranus was pointed almost directly at the Sun. The South Pole was experiencing continuous sunlight and had been for more than 20 years. The North Pole was in continuous darkness and had been for the same period. Both the pole that was sunlit and the equatorial regions that were experiencing normal day-night cycles were approximately the same temperature. This was unexpected. The expectation would be that the continuously sunlit pole would be significantly warmer than the equatorial regions that were experiencing day-night cycles, because the pole was receiving significantly more cumulative solar energy. But the temperatures were roughly equal. Uranus's atmosphere was transporting heat efficiently enough to distribute it around the planet, despite the extreme seasonal input pattern. The specific mechanism of this heat distribution is connected to the same mystery as Uranus's low internal heat output. The atmosphere of Uranus behaves differently from the atmosphere of Neptune despite the similar compositions and sizes of the two planets. Uranus transports heat efficiently laterally but not vertically. The interior of Uranus is not releasing its internal heat into the atmosphere at the rate that Neptune's interior does. The 2023 Decadal Survey's prioritization of a Uranus orbiter reflects the recognition that these questions are fundamental. Uranus is not simply one more gas or ice giant. It is an anomaly. It does not fit neatly into any of the categories that planetary science uses to classify worlds, and the specific ways it fails to fit contain information about the processes of planetary formation and evolution that a single flyby cannot reveal. A Uranus orbiter would spend years in the Uranian system. It would observe multiple seasons as Uranus progresses through its 84-year orbit. It would map the magnetic field in detail over the full orbital period. It would characterize the moons in detail that Voyager 2's 6-hour encounter could not approach. It would send a probe into the atmosphere to measure the composition and temperature profile directly. The scientific return from such a mission would be extraordinary, not because Uranus is spectacular in the way Jupiter is spectacular, a dramatic visual presence with its great red spot and its bands and its active volcanic moons. Uranus is less visually dramatic. But the questions it poses are fundamental. Why does it roll? The leading hypothesis is a large impact early in the solar system's history that tipped the planet on its side. But the properties of such an impact that would produce the current configuration without destroying the planet are specific enough to seem unlikely, and models of the accretion process have difficulty reproducing Uranus's exact configuration through a single impact. Why does it not radiate internal heat? The heat that Uranus should have retained from its formation is not escaping at the rate it should. Either Uranus is as typically cool for its size and formation history, or something is trapping its internal heat. Why does its magnetic field look the way it does? The offset, tilted magnetic field that Voyager 2 revealed has no analogue in the solar system, and no clear explanation in the current understanding of how planetary magnetic fields are generated. These questions have been waiting since 1986. They are still waiting. Voyager 2 also confirmed that Uranus has rings. They had been discovered telescopically in 1977, the same year Voyager launched, when Uranus occulted a star, and the star's light blinked on and off in a pattern consistent with ring material on both sides of the planet. Voyager 2 confirmed the 9 known rings, and discovered 2 more, and found that the rings were composed of dark material rather than the bright ice of Saturn's rings. The magnetic field of Uranus produced the most surprising discovery of the encounter. The magnetic poles of Uranus are not near the rotation poles. They are offset by approximately 59 degrees from the rotation axis, and are displaced from the planet's geometric center by about 1/3 of the planet's radius. This is bizarre. Earth's magnetic field is generated in the outer core and is roughly aligned with the rotation axis. No model of planetary magnetic field generation predicted a field so strongly offset from both the rotation axis and the geometric center. Uranus and Neptune share this oddity, but the discovery at Uranus was the first indication that something fundamentally different was happening in the interiors of the ice giants compared to the gas giants. The interior of Uranus remains poorly understood. The planet has a deep atmospheric layer, and beneath it, a region of compressed icy material, water and ammonia and methane under enormous pressure, and a small rocky core. The dynamics of that interior, the reason for the extreme tilt, the mechanism generating the offset magnetic field, the explanation for why Uranus radiates almost no internal heat compared to Jupiter and Neptune, these are open questions. Open because we have one dataset, one flyby, January 1986. Voyager 2 added its Uranian velocity boost and headed toward the outermost planet. 3.5 years to Neptune. 3.5 years through the outer solar system to the last stop of the Grand Tour. The things waiting at Neptune were, if anything, stranger than what Uranus had offered. Neptune is the most remote major planet in the solar system. At the time of Voyager 2's arrival on August 25, 1989, Neptune was approximately 4.4 billion kilometers from Earth. The signal travel time was nearly 6.5 hours each way. Instructions sent from Mission Control at JPL in Pasadena took 6.5 hours to reach the spacecraft. Data returned from the spacecraft took 6.5 hours to arrive on Earth. The entire closest approach sequence, the most critical and scientifically dense period of the encounter, ran on pre-programmed sequences stored in the spacecraft's onboard computers, because there was no possibility of real-time control at that communication delay. The spacecraft had been reprogrammed from Earth during the 4-year journey from Uranus to Neptune, because the science team had learned from the Uranus encounter what adaptations to make. The imaging protocols, the scan platform movements, the data compression algorithms, all were updated by radio commands that took hours to reach the spacecraft, and confirmations took hours to return. Neptune had been expected to be another Uranus, a featureless ice giant with a quiet atmosphere and a boring surface. It was not. Neptune's atmosphere, when Voyager 2's cameras resolved it, was full of structure, dynamic, moving, visibly active structure. A large dark oval feature in the southern hemisphere, dubbed the Great Dark Spot by analogy to Jupiter's Great Red Spot, was as large as Earth and showed evidence of being a persistent storm system, with winds circulating around it at hundreds of kilometers per hour. The winds on Neptune are the fastest in the solar system. The jet streams in Neptune's atmosphere move at approximately 2,100 kilometers per hour in the retrograde direction, opposite to the planet's rotation. For comparison, the fastest sustained winds on Earth, in the most powerful hurricanes, reach approximately 300 kilometers per hour. Neptune's wind speeds are 7 times that. In a planet 20 times farther from the Sun than Earth, receiving solar energy at less than 1,000th of Earth's solar flux, winds at these speeds require an explanation. The explanation is Neptune's internal heat. Unlike Uranus, which radiates almost no internal heat, Neptune radiates about 2.6 times the energy it receives from the Sun. Neptune has an internal heat source, the remnant heat from its formation, or some ongoing mechanism of heat generation, that drives its atmospheric dynamics in a way that Uranus's almost entirely solar-driven atmosphere cannot match. The two planets formed in similar regions of the protosolar disk are composed of similar material, and yet one is dynamically active and the other is calm by comparison. This contrast remains one of the unsolved puzzles of the outer solar system. Why does Neptune have internal heat, and Uranus does not? Or more precisely, why does Uranus appear to have suppressed its internal heat so efficiently that almost none escapes? There are hypotheses. Some involve a layer of material in Uranus's interior that acts as a thermal barrier. Some involve the impact that tipped Uranus on its side, also having mixed the interior in a way that disrupted heat transport. None is definitive. The question is open. The Great Dark Spot itself is no longer there. When the Hubble Space Telescope pointed at Neptune in 1994, 5 years after Voyager 2's flyby, the Great Dark Spot was gone. A new dark spot had appeared in the northern hemisphere. Neptune's atmosphere is dynamic on timescales of years, not the centuries that Jupiter's Great Red Spot has persisted. The features Voyager 2 saw were real and were accurately measured, but they were snapshots of a changing system. The Neptune of 1989 was not the Neptune of 1994, and is not the Neptune of today. The story of Neptune's discovery is worth telling here because it connects the modern understanding of the outer solar system to the very beginning of the tradition of inferring the existence of unobserved planets from their gravitational effects on observed ones. In 1846, astronomers had been puzzled for decades by small discrepancies in the predicted and observed position of Uranus, which had been discovered by William Herschel in 1781. The discrepancies were too consistent to be measurement errors, and too systematic to be easily explained by the known gravitational perturbations of other planets. In 1845, Urbain Le Verrier in France and John Couch Adams in England independently worked out the mathematics of where an undiscovered planet would need to be to produce the observed discrepancies in Uranus's orbit. Le Verrier communicated his prediction to Johann Gottfried Galle at the Berlin Observatory. Galle found Neptune on September 23, 1846, within 1 degree of the predicted position. Neptune is the first planet in the solar system to have been predicted mathematically before it was observed. Every other planet was first seen and then studied. Neptune was first calculated and then found. This was a triumph of Newtonian mechanics and mathematical astronomy, a demonstration that the equations describing gravitational interaction were accurate enough to point a telescope at a blank patch of sky and find an unknown world. Voyager 2's encounter with Neptune 143 years later was a different kind of triumph. Not the mathematical inference of a world's existence, but the direct observational characterization of a world whose existence had been confirmed but whose nature was almost entirely unknown. The closest approach distance of 4,950 kilometers above the cloud tops, chosen to allow a close encounter with Triton on the outbound trajectory, was by far the closest any Voyager had passed to any planetary atmosphere. The Neptune encounter was the most audacious of the 4 Voyager planetary encounters, and it produced the most dramatic discoveries. The wind speed of 2,100 km per hour is the fact that most requires emphasis because it is the most counterintuitive. Neptune receives less than 1% of the solar energy that Earth receives. It is a cold, dim world at enormous distance from the Sun. The conventional expectation would be a quiescent atmosphere, the way Uranus's visible disk was featureless. Instead, Neptune has the most energetically active atmosphere in the solar system, with the fastest winds and the most dramatic storm systems. The answer is internal heat. Neptune is releasing heat from its interior at a rate that supplements the low solar input and drives atmospheric dynamics. But why Neptune has this internal heat and Uranus does not remains the defining open question of ice giant science. The Triton discovery deserves its own extended treatment, because Triton is not simply a moon. It is a class of object that we have now characterized as another body. Pluto, visited by the New Horizons spacecraft in 2015, is similar in size to Triton, composed of similar material, formed in the same region of the solar system. The Pluto flyby, building on what Voyager 2 revealed about Triton, allowed comparison between two Kuiper Belt objects, one of which had been captured into planetary orbit and one of which remained in the outer solar system. Triton's surface showed a combination of ancient cratered terrain and younger smooth nitrogen ice deposits. The geysers of nitrogen erupting from the surface produced dark streaks extending for hundreds of kilometers downwind, creating patterns that are visible in the Voyager 2 images as dark tracings across the pale pink nitrogen ice. The mechanism driving the geysers, solar heating through the transparent nitrogen ice, requires sunlight to reach through the ice and heat darker material beneath. At Neptune's distance from the Sun, with sunlight approximately 0.1% of Earth's solar flux, the heating is extraordinarily slow, but cumulative enough to drive eruptions. The retrograde orbit of Triton is responsible for the gradual decay toward the Roche limit, but it also has an interesting consequence for Triton's history. When Triton was captured, its original orbit was almost certainly highly eccentric, taking it close to Neptune, and then far away on a long elliptical path. Tidal friction circularized this orbit over billions of years. During the circularization process, Triton would have experienced intense tidal heating, comparable to or exceeding what Io experiences today. The early Triton may have been a volcanically and geologically active world. Today's Triton is the quiet remnant of that earlier violent history. Triton is the discovery that matters most from the Neptune encounter. Triton is Neptune's largest moon, approximately 2,700 kilometers in diameter, roughly the size of Earth's moon. It was discovered in 1846, just 17 days after Neptune itself was discovered. For over a century, the most notable fact known about Triton was that it orbits Neptune in the retrograde direction, opposite to Neptune's rotation and opposite to the direction of orbit of almost every significant moon in the solar system. This retrograde orbit was the first strong evidence that Triton did not form around Neptune, but was captured by Neptune's gravity at some point in the past, in an orbit that carried it in the wrong direction relative to the planet's own spin. The capture process is complex and requires specific conditions to work. The captured body must lose enough energy to become gravitationally bound to Neptune without being destroyed. The most likely mechanism involves a binary object, two bodies orbiting each other, encountering Neptune and having one of them captured while the other escapes. The retrograde orbit has a specific long-term consequence. Tidal interactions between Neptune and Triton are causing Triton's orbit to spiral inward. Slowly, over billions of years, Triton is getting closer to Neptune. In approximately 3.5 billion years, Triton will cross Neptune's Roche limit, the distance at which Neptune's tidal forces exceed Triton's own gravity, enough to pull it apart. When that happens, Triton will be destroyed and Neptune will acquire a ring system far more spectacular than anything it currently has. Triton's surface, when Voyager 2 resolved it, was extraordinarily cold. The surface temperature was approximately -235 degrees Celsius, making Triton one of the coldest surfaces in the solar system. The coldness comes from Triton's highly reflective surface. It reflects about 70% of incoming sunlight, leaving very little to absorb and convert to heat. Triton's surface was also active. Voyager 2 detected geysers on Triton, not volcanoes, geysers of nitrogen gas, erupting from the surface and rising several kilometers into the thin atmosphere before the nitrogen condensed and fell back as dark streaks on the surface. The mechanism is solar-driven. Sunlight penetrates the thin, transparent layer of nitrogen ice on Triton's surface and heats the darker material beneath. The trapped heat vaporizes nitrogen, which builds up pressure and eventually erupts through the ice above. The geysers of Triton are driven by the faint light of a sun that is 30 times farther away than it is from Earth. They are geysers powered by sunlight so weak that it amounts to roughly 1/1000th of what Earth's surface receives. They erupt from a surface colder than liquid air. They are one of the stranger phenomena in the solar system, and Voyager 2 saw them, once, in passing. After the Neptune encounter, Voyager 2's trajectory carried it below the ecliptic plane, out of the plane in which the planets orbit. This was the final consequence of the Grand Tour trajectory. Having used Neptune's gravity to swing itself one last time, Voyager 2 was now on a path that would take it south of the solar system as seen from above. The Grand Tour was complete. Jupiter, Saturn, Uranus, Neptune. 48 moons observed in total across the four systems, multiple ring systems studied, active volcanism confirmed on Io, subsurface ocean evidence found at Europa. Extraordinary geology discovered on Miranda, the fastest winds in the solar system measured at Neptune, geysers observed on Triton. And then, a very long silence punctuated by weak signals crossing the growing distance as the spacecraft moved away from the last planet. But the journey was not over. The solar system extended far beyond Neptune, and Voyager 2 had more to cross before it could be called done. Beyond Neptune, the solar system continues for a very long time. The classical solar system, the 8 planets, and their moons and the asteroid belt fits within a sphere approximately 60 astronomical units across, 60 times the Earth-Sun distance. Neptune orbits at about 30 astronomical units. The Kuiper Belt, the region of icy bodies that extends from Neptune's orbit outward to about 50 astronomical units, contains Pluto and hundreds of thousands of smaller objects. Beyond the Kuiper Belt, the scattered disk extends further, with objects on eccentric orbits that swing between the inner Kuiper Belt and hundreds of astronomical units. Beyond the scattered disk, beginning at roughly 2,000 astronomical units and extending to perhaps 100,000, is the Oort cloud, a spherical shell of icy bodies whose existence was proposed theoretically by Jan Oort in 1950, and which is inferred from the orbits of long-period comets, but has never been directly observed. The heliosphere, the bubble of solar wind that inflates the immediate environment of the solar system with charged particles from the Sun, extends to roughly 120 astronomical units on the upstream side facing the direction of the solar system's motion through the galaxy. The boundary of the heliosphere is the heliopause. Voyager 2 crossed the heliopause on November 5, 2018, 41 years, 2 months and 15 days after launch. The crossing was confirmed when the plasma science instrument on Voyager 2 detected an abrupt increase in plasma density, consistent with the higher density interstellar plasma that exists beyond the heliopause. The plasma inside the heliosphere is hot and tenuous, diluted by expansion from the Sun. The plasma in the interstellar medium is denser and cooler. The transition was sharp enough to identify a specific date of crossing. The specific date is significant because it is different from Voyager 1's crossing. Voyager 1 crossed the heliopause in August 2012, about 6 years earlier, even though Voyager 2 is farther from the Sun in terms of years of travel time. The difference reflects the asymmetry of the heliosphere. Voyager 1 crossed in the upstream direction, the direction the heliosphere is compressed by ram pressure from the interstellar medium. Voyager 2 crossed in the flank direction, where the heliosphere is broader and the boundary farther from the Sun. This meant that Voyager 2's crossing provided information about a different region of the heliopause than Voyager 1's crossing. The two crossings, 6 years apart and at different distances from the Sun, reveal that the heliosphere is asymmetric and that the conditions at the heliopause vary with location. This comparison was only possible because two spacecraft happened to be traveling in different directions. Voyager 2's plasma science instrument also detected that the plasma temperature in the interstellar medium was higher than models had predicted, and that the density of neutral hydrogen atoms was higher than expected. These measurements confirmed and refined models of the local interstellar medium that had previously been based on less direct observations. The heliopause crossing in 2018 is worth examining in more detail because what Voyager 2 found there was not exactly what models had predicted, and the differences are scientifically significant. The heliopause is the boundary between the heliosphere, the bubble of solar wind plasma that surrounds the solar system, and the interstellar medium. It is not a sharp boundary in the way that the surface of a planet is sharp. It is a transition zone, a region where the solar plasma and the interstellar plasma are in pressure balance, where each is trying to push the other back and succeeding approximately equally. The exact shape and location of this boundary depends on the properties of both the solar wind and the interstellar medium. When Voyager 1 crossed the heliopause in 2012, it detected an abrupt decrease in the solar particle flux and an increase in cosmic ray flux from the galaxy, consistent with transitioning from the solar-dominated heliosphere to the galactic-dominated interstellar medium. The magnetic field direction changed, as expected for the transition from the solar magnetic field to the interstellar field. The crossing was relatively sharp in the data. Voyager 2's crossing in 2018 showed some similarities and some differences. The decrease in solar plasma and the increase in galactic cosmic rays were similar. But the plasma temperature in the heliosheath, the region just inside the heliopause, appeared different at Voyager 2's crossing location than at Voyager 1's, suggesting that the heliosphere is not uniform in its properties. The direction Voyager 2 was travelling, southward of the ecliptic and at a different azimuthal angle from Voyager 1, meant it was sampling a different part of the heliopause boundary. One of the more surprising findings from Voyager 2's crossing was the detection of a thin layer of hot plasma just inside the heliopause that was not expected from pre-crossing models. This layer, where the plasma temperature was significantly higher than expected, suggested that some process is heating the plasma near the heliopause boundary in ways that models had not accounted for. Understanding this layer requires theoretical work that is ongoing. The comparison between Voyager 1 and Voyager 2 at the heliopause is one of the great serendipitous science opportunities in the history of the Voyager program. 2 spacecraft launched simultaneously, following different trajectories for 41 years, crossing the heliopause at different locations 6 years apart. The comparison reveals that the heliosphere is asymmetric, and that the boundary conditions vary with location and direction. No spacecraft other than Voyager 1 and 2 has ever crossed the heliopause. No spacecraft is currently on a trajectory to cross it in any near-term future. The New Horizons spacecraft, which visited Pluto in 2015, and a Kuiper Belt Object in 2019, is on a trajectory that will eventually cross the termination shock and possibly the heliopause, but not for several decades. The local interstellar medium that Voyager 2 is now sampling is a specific and unusual region called the local interstellar cloud, or the local fluff. This cloud, roughly 30 light-years across, is a region of warm, partially ionized hydrogen that the solar system has been moving through for the past 100,000 years or so. The properties of this cloud determine the conditions at the heliopause and affect the degree to which the interstellar medium interacts with the solar wind. Understanding the local interstellar cloud matters for understanding the long-term history of the solar system's environment. The cloud will not last forever. The solar system will eventually move into a different region of the interstellar medium with different density and temperature. The specific properties of the cosmic ray environment, the magnetic field, and the neutral particle flux that have characterized the solar system's interstellar neighborhood for the past 100,000 years will change. The Voyager spacecraft are the only instruments we have ever placed in that interstellar neighborhood. What they measure is unique. What they will continue to measure until the power runs out is data that cannot be obtained by any other means currently available. As of 2024, Voyager 2 is approximately 22 billion kilometers from the Sun, or about 130 astronomical units, and is moving at approximately 15.4 kilometers per second relative to the Sun. It is in the direction of the constellation Telescopium. The signal from Voyager 2 traveling at the speed of light takes roughly 20 hours to reach Earth. The power from its radioisotope thermoelectric generators has been declining since launch as the plutonium-238 decays. At launch, the RTGs produced approximately 470 watts. By the 2020s, the output had fallen to roughly 250 watts. The power management has required the mission team to progressively shut down instruments and heaters to keep the most important science instruments operational. In 2020, NASA engineers discovered that a power fault protection mechanism had autonomously switched off a science instrument to protect the power system. They were able to restore the instrument and continue science operations, but the incident illustrated how close to the margins the spacecraft now operates. Each instrument that remains operational does so within an increasingly tight power budget. The instruments that matter most for the ongoing scientific mission are those measuring the local interstellar medium, the magnetic field instrument, the plasma wave system, the low-energy charged particle instrument, the cosmic ray system. These are sampling a region of space that no other spacecraft has ever visited, and that no spacecraft is currently on track to visit in the foreseeable future. The plasma science instrument on Voyager 2, unlike the equivalent instrument on Voyager 1 which stopped working in 1980, is still operational. This makes Voyager 2 the only spacecraft currently capable of directly measuring the interstellar plasma, and the measurements it makes are unique. Eventually, the power will fall below the minimum required to operate any instrument. The signal will grow too weak to detect. The spacecraft will continue moving, following the trajectory that physics has assigned it, but it will do so in silence. The specific moment of final silence is uncertain and depends on which instruments are kept operational and how the power curve evolves. But the current estimates place it in the 2030s. After the silence, the trajectory continues. Voyager 2 will not reach the nearest star. It is not aimed at the nearest star. It is aimed in the direction of Telescopium, a faint southern constellation. In approximately 40,000 years, it will make its closest approach to another star. Ross 248, a red dwarf currently about 10.3 light-years away, will pass within about 1.76 light-years of Voyager 2's trajectory. This is still an enormous distance, far too large for any gravitational interaction of consequence, but it represents the nearest approach to any stellar system that Voyager 2's current trajectory will achieve in any reasonable planning horizon. Like Voyager 1, Voyager 2 carries a golden record. The gold-plated copper disk with its sounds of Earth and its 116 images and its 55 languages and its 90 minutes of music. The record that was intended, however improbably, to be found by something that could read it. Voyager 2's record carries some of the same content as Voyager 1's. The same pulsar map, the same hydrogen diagram, the same calibration image as the first picture in the sequence. But it carries its own specific selection of music and greetings, chosen slightly differently from Voyager 1's selections by the same committee under Carl Sagan's direction. Two golden records, moving in different directions through interstellar space. Two bottles thrown into the cosmic ocean by a species that was not sure anyone would ever find them, but threw them anyway because the not knowing was better than the not trying. Voyager 2 is still going. It will be going for a very long time. The specific question of what it means that Uranus and Neptune have each been visited only once, and only by a spacecraft with 1970s technology, takes on additional significance when you consider the role these planets play in our broader understanding of planetary systems. The discovery of exoplanets over the last 3 decades has fundamentally changed the context for solar system science. We now know that planets are extraordinarily common in the galaxy. We know that the most common class of planet around other stars by number is a planet with a mass between Earth and Neptune, sometimes called a super-Earth or mini-Neptune. These planets, which range from roughly 2 to 17 Earth masses, orbit the majority of nearby stars that have planets at all. Our solar system does not have a planet in this mass range. Earth is roughly 1 Earth mass. Neptune is roughly 17. There is nothing in between. This gap in our solar system has been noted as a potential indication of an unusual dynamical history, one of the ways our solar system may differ from the typical planetary system. But Uranus and Neptune are ice giants, not gas giants, and they occupy the lower end of the giant planet size range. They're closer to being mini-Neptunes than to being Jupiters. Studying Uranus and Neptune, understanding their composition and their internal structure and their formation history, is directly relevant to understanding the most common class of planet in the galaxy. The ice giants of our solar system are the closest analogues to the most common type of exoplanet. Every piece of understanding we develop about Uranus and Neptune applies, with appropriate modifications, to the hundreds of millions of similar-sized planets in the Milky Way. Every question about the interior structure of Uranus, every question about the atmospheric dynamics of Neptune, every question about the formation of ice giants as a class, has implications that extend far beyond our own solar system. This is the scientific context in which the lack of follow-up missions to Uranus and Neptune is most troubling. We have a detailed understanding of our gas giants, Jupiter and Saturn, from decades of orbital missions. We have almost no detailed understanding of our ice giants from a single flyby each, and ice giants are, quantitatively, the most important class of planet in the galaxy. Voyager 2 opened the door. It showed us that these worlds are extraordinary, that they contain puzzles that challenge our models, that they have moons with active geology, and atmospheres with dynamics we do not understand. It took the first photographs of worlds that had been points of light for all of human history before 1986. That opening has not been followed by the investigation it deserves. The Decadal Survey's recommendation and the scientific community's consensus that a Uranus mission is the highest priority large planetary science mission represents a recognition that the gap in our knowledge of ice giants is not just a gap about our solar system. It is a gap about planetary science as a discipline, about our ability to understand the most common type of world in the galaxy. Voyager 2 is now in interstellar space, moving away from Uranus and Neptune at 15 kilometers per second. It will not return. No one can change its trajectory or update its instructions in any meaningful way at the communication delays involved. The invitation to return to these worlds belongs to a different machine, one that is designed specifically for orbital science at Uranus, with modern instruments, modern communication bandwidth, modern power systems, and the ability to spend years rather than hours in the Uranian system. That machine does not yet exist. But Voyager 2 showed us why it should. There is something specific that happens when you trace the Voyager 2 mission from beginning to present, and it is worth naming before the close. The history of planetary exploration is largely a history of follow-up. We found something interesting at Mars in the 1970s, and we sent orbiters and landers and rovers in every subsequent decade. We found something interesting at Jupiter in 1979, and we sent the Galileo orbiter in 1989 and the Juno orbiter in 2011. We found something interesting at Saturn in 1981, and we sent the Cassini-Huygens mission, which arrived in 2004 and spent 13 years in the Saturn system, before deliberately diving into the planet's atmosphere in 2017 to protect the moons from contamination. The pattern is preliminary survey, extraordinary discovery, follow-up mission, detailed characterization. For Uranus and Neptune, the follow-up mission does not exist. Voyager 2 passed Uranus in January 1986. It passed Neptune in August 1989. These were extraordinary scientific achievements. They transformed our understanding of two entire planets and their moon systems. They raised fundamental questions about planetary formation, interior structure, atmospheric dynamics, moon geology, and the diversity of icy worlds in the outer solar system. Those questions are still open, not all of them. Some have been partially answered by Earth-based and space telescope observation. Some have been addressed through modelling and theoretical work. But the fundamental questions that only a spacecraft at Uranus or Neptune can answer, questions about the interior structure, the detailed atmospheric dynamics, the subsurface conditions of the moons, the complete census of ring structures, have not been answered and will not be answered until a mission is sent. Proposals have been made. The Planetary Science and Astrobiology Decadal Survey, 2023 to 2032, published by the National Academies of Sciences, Engineering and Medicine, recommended a Uranus orbiter and probe as its highest priority large mission, surpassing even an Enceladus mission and a Mars sample return campaign. This was a strong recommendation from the scientific community that Uranus specifically is the highest priority destination in the solar system for a flagship-class mission. Whether this recommendation is funded and acted on depends on NASA budgets, launch opportunities, and the political will to commit to a mission that would take roughly a decade to develop, and then another decade or more in transit before returning science. The Uranian year is 84 Earth years. A mission that arrived at Uranus could observe a significant fraction of the Uranian seasons that Voyager 2, passing in approximately 6 hours, could not sample. Neptune is a lower priority in the current decadal survey than Uranus, but the scientific case for a Neptune orbiter and Triton lander is also strong. Triton is a captured Kuiper Belt object, and studying it in situ would give us direct access to the composition and geology of the same class of objects as Pluto, which was visited by the New Horizons spacecraft in 2015. Triton is larger than Pluto and has an active surface and an atmosphere. A Triton lander would be one of the most scientifically extraordinary missions ever flown. As of 2024, neither mission is in development. Both are concepts. Both have community support. Neither has funding. This means that the Voyager 2 dataset from 1986 and 1989 remains the primary close-range dataset for 2 of the 8 planets in our solar system. not supplemented by follow-up missions, not being compared to updated observations from orbiters. The primary dataset, roughly 40 years old, taken during a single pass that lasted hours. This is what the Voyager 2 mission means in full. It is not only a triumph of engineering and navigation and science planning, it is a standing reminder of what we have seen once and never returned to, of worlds we know are extraordinary and have not gone back to, of questions Voyager 2 asked in 1986 that are still waiting for an answer because no one has yet built the machine to answer them. The close of the mission briefing is not a close of the scientific story, it is an invitation to go back to Uranus and its rolling seasons and its offset magnetic field and its geologically impossible moon Miranda with its cliff that drops 10 kilometers into a world we understand only in silhouette. To Neptune and its impossible winds and its captured moon spiraling toward eventual destruction, and its nitrogen geysers and its great dark spot that appeared and disappeared before any follow-up mission could study it. To the questions that have been waiting since 1986 and 1989 for someone to build the next spacecraft. The invitation is real. The worlds are still there. The questions are still open. And Voyager 2, moving through the interstellar medium at 15 kilometers per second, is not going to send back any more data from those worlds. It has done its part. The specific timeline of what Voyager 2 passed, stated plainly and in sequence, is worth spelling out because the accumulated totality is more than any summary conveys. August 20th, 1977, launch from Cape Canaveral. Aboard, a 722-kilogram spacecraft carrying 11 science instruments, a radioisotope thermoelectric generator, and a golden record. December 10th, 1977, crossed the asteroid belt. The asteroid belt is not the dense debris field of science fiction. It is an enormous volume of space containing billions of objects whose total mass adds up to approximately 4% of the Moon's mass. Voyager 2 crossed it without incident, which is the expected outcome. The probability of hitting any significant asteroid while crossing the belt, even over the months required to transit it, is very low. July 9th, 1979. Closest approach to Jupiter. Distance, 570,000 kilometers. Confirmed active volcanism on Io. Found evidence for subsurface ocean on Europa. Measured the Great Red Spot's winds at over 600 kilometers per hour. Discovered 3 new small moons. Confirmed Jupiter's ring system discovered by Voyager 1 4 months earlier. August 26th, 1981. Closest approach to Saturn. Distance, 101,000 kilometers. Characterized the ring system at resolutions unachievable from Earth. Found that Saturn's rings are in some places only 20 meters thick across a radial span of 73,000 kilometers. Observed evidence of geological activity on Enceladus. Characterized Titan's thick atmosphere in the optical. January 24th, 1986. Closest approach to Uranus. Distance, 81,500 kilometers. First spacecraft ever to visit Uranus. Discovered 10 new moons, bringing the then-known total to 27. Discovered 2 new rings, bringing the total to 11. Found that Uranus's magnetic field is offset by 59 degrees from its rotation axis and displaced from the planet's center. Observed Verona Rupes on Miranda, the tallest known cliff in the solar system at approximately 10 kilometers. August 25th, 1989. Closest approach to Neptune. Distance, 4,950 kilometers above cloud tops. First spacecraft ever to visit Neptune. Measured winds at 2,100 kilometers per hour, the fastest in the solar system. Observed the Great Dark Spot, a storm system as large as Earth, which no longer exists. Observed geysers of nitrogen erupting from the surface of Triton. Discovered 6 new moons. Confirmed that Triton is in a retrograde orbit consistent with capture. February 14th, 1990. The pale blue dot photograph. This was taken by Voyager 1, not Voyager 2, but it is worth noting the approximate date as a temporal marker. By this point, Voyager 2 was approximately 3 billion kilometers from Earth and had completed all 4 planetary encounters. 1990 to 2018, 28 years of transit through the outer heliosphere, the Helios Heath, and the termination shock, measuring the properties of the solar wind as it slows and is compressed by the interstellar medium. Instruments failing one by one, power declining. The mission team progressively reducing heater power, shutting down subsystems, concentrating remaining power on the most scientifically valuable instruments. November 5th, 2018. Crossed the heliopause, entered interstellar space. Became the second human-made object to cross into the interstellar medium. 2018 to present, sampling the local interstellar medium. Measuring plasma density, magnetic field, cosmic ray flux. The only operating spacecraft with a functional plasma science instrument in the interstellar medium. Approximately 2030s, estimated time of final signal. The specific date is uncertain and depends on power management decisions not yet made. 40,000 years from now. Closest approach to Ross 248 at approximately 1.76 light years. Roughly 296,000 years from now, closest approach to Sirius at approximately 4.3 light years. The timeline from launch pad to the far future of the galaxy is a single continuous trajectory, determined by the physics of the original launch and the subsequent gravity assists, modified infinitesimally by each course correction burn, and then fixed forever when the propellant runs out. Voyager 2 is still on that trajectory. Everything it has passed once. Everything it is approaching, it will approach once. There is no turning back. The question of what we have learned from Voyager 2 that we could not have learned any other way requires being specific, because some of the mission's science could eventually have been done by subsequent missions and some of it is intrinsically about being there at that moment. The intrinsically irreplaceable data are the observations of phenomena that exist at a single point in time. The Great Dark Spot on Neptune existed in 1989. It does not exist now. No mission that visits Neptune today, whether it arrives in 2040 or 2060, will see the Great Dark Spot. It is gone. Voyager 2's observations of it, imperfect and brief as they were, are the only direct observations that will ever exist of that specific storm system. If we want to understand what caused the Great Dark Spot, how it was maintained, why it eventually dissipated, we have one data set, one flyby, hours of observation from a single geometric perspective. The same is true of the specific volcanic state of Io in 1979. The volcanoes Voyager observed were active at that moment. The specific eruption columns, the specific lava flows, the specific patterns of sulfur deposits on the surface. These were the Io of 1979. Io is still volcanically active and has been observed by subsequent missions including Galileo and Juno. But the Io of 1979 is gone, its surface continuously overwritten by new eruptions, and only Voyager's images preserve what it looked like then. Triton's geysers, observed by Voyager 2, have not been confirmed in detail by any subsequent observation, because no subsequent mission has been close enough to Triton to observe them. The geysers were predicted to be active from the Voyager data and from the mechanism of solar heating through transparent nitrogen ice. Whether they are currently active, whether the specific geyser locations Voyager mapped are still erupting, whether the plume heights and downwind streaks have changed, we do not know. We have Voyager 2's data from 1989 and nothing else. The heliopause crossing in 2018 is another example of intrinsically irreplaceable data. The heliopause was not at the same location in 2018 as it would have been in 2000 or will be in 2040. The heliopause moves in and out with the solar cycle and with the long-term variation of solar activity. The crossing Voyager 2 made was a crossing at a specific time, in a specific direction, under specific solar wind conditions. Any subsequent spacecraft crossing the heliopause in the same direction will cross it under different conditions at a different location, and the comparison will be informative but not a repeat of what Voyager 2 found. The lesson of Voyager 2, repeated across every encounter, is that the universe does not offer second looks at the same moment. What exists at a given place at a given time exists only then. The data taken is irreplaceable. The data not taken is permanently lost. This is not a reason for despair. It is the reason why continued investment in planetary exploration is not redundant even when earlier missions have visited the same destinations. The Neptune of the 2040s will be different from the Neptune of 1989. The Uranus of the 2030s, when or if a dedicated orbiter reaches it, will be different from the Uranus of 1986. Each visit sees a different moment. Each moment is worth recording. But the first visit is a specific kind of irreplaceable. It is the first time human instruments ever pointed themselves at a world and said, Let us see what is actually here, not what we predicted, not what models suggested, what is actually here. Voyager 2 said this to Jupiter, to Saturn, to Uranus, to Neptune, to the helioceith, to the interstellar medium, and in each case the answer was stranger and more complex than the question had been. That is the specific kind of discovery that earns the word great. And Voyager 2 has earned it 47 years into a journey that will continue long after everyone who designed it is gone. There is one last thing about the Voyager 2 mission that does not usually receive adequate attention in accounts of the mission, and it concerns the people who built it. Voyager 2 was designed by engineers and scientists who were working at the edge of what was technically possible in the early 1970s. The spacecraft was designed before personal computers existed. The flight software was written for computers with kilobytes of memory. The instruments were designed for miniaturization that was at the absolute frontier of 1970s technology. The communication system was designed to transmit data across distances of billions of kilometers using technology that was, at the time, new. And they built it to work, not just to work for the mission design lifetime of 4 years through the Jupiter and Saturn encounters. They built it to work for 47 years and counting. The spacecraft has operated in temperatures ranging from the sun-warmed environment of the inner solar system to the frigid interstellar medium. Its instruments have been exposed to the radiation belts of Jupiter and the quiet of interstellar space. Its electronics have experienced the thermal cycles of passing in and out of planetary shadows and the gradual, relentless decline of power from the RTGs. The attitude control thrusters have fired thousands of times to keep the antenna pointed at Earth. The specific engineering decisions made by people who in many cases are no longer alive have kept the spacecraft operational through conditions that no spacecraft had ever been built to survive, in an environment that no spacecraft had ever travelled through, across timescales that exceeded the expected lifetimes of many of the components. The mission operations team at JPL, the current generation of engineers and scientists who receive and interpret Voyager 2's signals, is largely different from the team that designed the spacecraft. They are stewards of a mission that is older than most of them. They maintain contact with a spacecraft that was built before they were born using software running on the spacecraft that reflects decisions made by their professional predecessors. The institutional knowledge that allows them to do this has been transmitted across generations of JPL staff through documentation and mentorship and the specific culture of a team that understands what it holds. When the signal finally goes quiet, when the RTG power drops below the threshold required to operate any instrument, and the spacecraft falls silent, the people who will be at JPL to receive the last signal will be people who had no part in building the machine. The generation that built it is largely gone. The generation that witnessed the planetary encounters is mostly retired, but the spacecraft is still there, still moving, still transmitting, in the 2020s, signals that carry science from the interstellar medium back to a collection of antennas in California and Spain and Australia, whose combined sensitivity can just barely pick up a signal that has crossed 20 billion kilometers at a power of 22 watts, arriving with less energy than it takes for a snowflake to hit the ground. That is the human achievement at the center of the mission, not just the science. The fact that a machine built with 1970s technology and launched nearly half a century ago is still telling us things we did not know about the universe we live in. It is the longest continuous science mission in human history, and it is still running. Io deserves an extended section, because the discovery of its volcanism in 1979 was one of the most significant moments in the history of planetary science, and the full significance of what was found is easy to understate. Before Voyager, the assumption in planetary science was that geological activity, volcanism, tectonics, cryovolcanism, required a sufficiently large body to retain internal heat from formation and from radioactive decay. Small bodies were expected to be cold and geologically dead. The Moon, with a radius of 1,737 kilometers, had been geologically active billions of years ago but had cooled and quieted. Mars, larger than the Moon, showed evidence of past volcanic activity, including the enormous shield volcano Olympus Mons, but the activity was believed to have ceased hundreds of millions of years ago. Io, at 1,821 kilometers radius, is only slightly larger than the Moon. Under the pre-Voyager model, Io should have been geologically dead. It was not. The discovery forced an immediate revision. The heat source for Io's activity is not primordial heat or radioactive decay, it is tidal. The energy comes from Jupiter's gravity, continuously flexing the interior of Io as it moves through a slightly eccentric orbit maintained by orbital resonances with Europa and Ganymede. This changed everything about how planetary scientists think about the potential for geological activity in the outer solar system. If Io can be tidally heated to the point of continuous active volcanism, then other bodies in the outer solar system with different tidal heating intensities might be warm enough for internal liquid water. Europa might have a liquid water ocean. Enceladus, discovered later by Cassini to have geysers and a subsurface ocean, is another example of tidal heating doing extraordinary things to a small body. The discovery of Io's volcanism was the beginning of a new understanding that habitable environments in the solar system are not limited to the narrow habitable zone where liquid water can exist on planetary surfaces. They extend wherever tidal heating provides the energy to maintain liquid environments beneath icy surfaces or within rocky mantles. This has become one of the central themes of astrobiology, the possibility that the most common habitable environments in the solar system, and perhaps in planetary systems generally, are not surface environments but subsurface environments maintained by tidal heating. Europa's ocean is the most compelling example in our solar system. Enceladus is another. The discovery of both traces back in the first instance to the volcanic plumes observed by Voyager 1 on Io in 1979 and confirmed by Voyager 2 4 months later. The specific details of Io's volcanism as Voyager 2 observed it are worth noting. The largest plume observed by Voyager 2 during the July 1979 encounter was Pele, named for the Hawaiian volcano goddess. Pele's plume reached approximately 300 kilometers above Io's surface and deposited a ring of sulfur and sulfur dioxide hundreds of kilometers in diameter around the vent. The red color of the deposited material, different from the yellows and oranges produced by other volcanic processes on Io, indicated a specific form of sulfur produced at particularly high temperatures. The eruption rate of Io's volcanoes collectively is estimated to resurface the Moon, with material at a rate of several millimeters per year averaged globally and much faster in the most active regions. The total rate of volcanic output from Io is comparable to the total rate from all of Earth's volcanoes combined, despite Io being only slightly larger than the Moon. Io's volcanic activity is not quiet or sporadic. It is the most intense geological activity anywhere in the solar system, far exceeding Earth's. Understanding why Io is so much more active than Earth, when both bodies are rocky worlds of roughly comparable size, is a matter of understanding the difference between solar heating and tidal heating as energy sources for geological activity. Solar heating drives Earth's plate tectonics only indirectly, through the uneven heating of the surface and the resulting convection that drives atmospheric and oceanic circulation. Earth's interior heat comes from radioactive decay and from the heat of formation. Io's interior heat comes primarily from Jupiter's gravity. The comparison between the two worlds is a comparison between two different mechanisms for maintaining a geologically active body. Both can produce volcanism, both can maintain liquid interiors. The mechanism is different, the output is comparable. The lesson is that geological activity does not require a large body in the inner solar system. It requires energy, and energy comes from multiple sources. The history of planetary science since 1979 has been substantially the history of exploring the implications of this discovery. Saturn's moon system deserves a separate extended discussion because the diversity it contains, from Titan's planet-like atmosphere to Enceladus's geysers to Iapetus's two-tone mystery, represents the full range of what icy moon environments can be. Voyager 2's encounter with the Saturn system in 1981 produced the first close-up images of Enceladus and the first hints that it was geologically unusual. The surface of Enceladus, only 500 kilometers in diameter, showed regions of fresh, uncratered ice that could only exist if the surface was being continuously renewed. The mechanism for renewal was not visible to Voyager 2. It would not be revealed until the Cassini mission arrived in 2004 and discovered geysers of water vapor erupting from the south pole of Enceladus, venting material from a subsurface liquid ocean into space. The story of Enceladus is in some ways the sequel to the story of Io. Io demonstrated that tidal heating could drive extreme geological activity in a small body. Enceladus demonstrated that tidal heating could maintain liquid water in a body so small and so cold that it seems impossible. Enceladus orbits Saturn in a resonance with Dione, the larger moon just outside it, and this resonance maintains a slight eccentricity that drives tidal heating in the interior. The heat is not enough to produce volcanism in the Io sense, but it is enough to maintain a liquid water ocean beneath the south polar ice. The geysers of Enceladus carry not just water, but organic molecules, molecular hydrogen, and the specific combination of energy sources and chemical complexity that astrobiologists consider necessary for habitability. The ocean of Enceladus is in contact with a rocky seafloor. The chemistry at that contact, driven by the water-rock interaction at hydrothermal vents, produces the conditions that, in Earth's oceans, host entire ecosystems at abyssal depths where sunlight never reaches. Voyager 2 saw Enceladus's smooth terrain. It did not see the geysers. The geysers were discovered 23 years later. But Voyager 2's observations of the unusual surface were the first indication that something extraordinary was happening there, an observation that motivated the more focused observation campaigns by Cassini that led to the discovery. Iapetus, the outermost of Saturn's major moons, presented a different mystery. It had been known since Giovanni Cassini's discovery in 1671 that Iapetus has a dramatically two-toned appearance. One hemisphere is bright, roughly as reflective as fresh snow, while the other is extremely dark as coal. The explanation for this striking contrast was debated for 3 centuries. Voyager 2's images of Iapetus showed the contrast sharply, but did not resolve the origin. The bright material is water ice. The dark material is complex organic material mixed with ice. The leading explanation is that the dark material is deposited from outside, from dust particles that Iapetus sweeps up as it orbits Saturn. The leading hemisphere, the side that faces in the direction of orbital motion, accumulates dark dust from the outer solar system, while the trailing hemisphere remains bright ice. The dark material then absorbs more sunlight and heats up, evaporating water ice from the dark regions, which migrates to the bright polar regions and refreezes. This cycle, called thermal migration, was eventually supported by Cassini observations and is now the accepted explanation. But the contrast existed for 3 centuries as an unexplained astronomical curiosity and was partially characterized by Voyager 2 before Cassini resolved it. The diversity of the Saturn moon system from world to world, from the volcanically featureless seeming Triton, to the extraordinarily active Enceladus, to the mysteriously two-toned Iapetus, to the ringed shepherd moons, to the heavily cratered Mimas, represents the full spectrum of what small icy worlds in a large planetary system can become. Each world has been shaped by a unique combination of its formation history, its compositional starting point, its relationship to Saturn's tidal field, its distance from Saturn's radiation belts, and the random chance of what large impacts it has experienced. Voyager 2 gave us the first look at this diversity. Cassini gave us a decade of detailed study. The picture that emerges is of a solar system that is far more various at the small world scale than any prior model had suggested. And Uranus and Neptune await, with their own moon systems, their own tidal heating regimes, their own histories of interaction between the planets and their satellites. The full picture of what icy moon diversity looks like in the outer solar system requires visiting ice giants, not just gas giants. Voyager 2 showed us what Uranus and Neptune's moon systems look like in rough outline. The details are still waiting to be filled in. The mission's relationship to the Golden Record is worth addressing directly, because the Golden Record is the element of the Voyager missions that speaks most directly to a question bigger than planetary science. Carl Sagan, who chaired the committee that designed the record, described it as a bottle thrown into the cosmic ocean. The metaphor is exactly right in its acknowledgement of improbability. The probability that Voyager 2's record is ever found by anyone or anything capable of reading it is extraordinarily small. The galaxy is vast, the spacecraft is tiny, and the trajectory does not approach any specific star for tens of thousands of years. But the record was not created primarily for the finder. It was created for the makers. The process of deciding what to put on the record, what images represented humanity, what sounds of Earth were essential, what music from across the world's cultures deserved inclusion, required the people making those decisions to ask a question they had never been formally asked. What is humanity, and what of it is worth preserving? The question does not have an easy answer. The committee that made the selections was aware that any selection was partial, culturally biased, and in some respects arbitrary. The music selected includes Beethoven and Bach, a Navajo night chant, a Georgian choir, Peruvian panpipes, a Senegalese percussion piece, Chuck Berry's Johnny Be Good, and Blind Willie Johnson's Dark Was the Night. The images include anatomical diagrams, the structure of DNA, a sunset with vegetation, ocean surf, a nursing mother, school children, the Great Wall of China. The sounds include a heartbeat, rain, wind, waves, a chimpanzee, and the spoken greetings of representatives of 55 languages. Every one of these choices reflects a judgment about what represents human life, and every judgment is contestable. The committee knew this. They made the choices anyway, because the alternative was sending nothing, and sending something, however imperfect the representation, was better than sending nothing. The record that Voyager 2 carries is a specific 1977 snapshot of what a committee of American scientists and cultural advisors thought was worth saying about humanity to whoever might eventually listen. It is not comprehensive, it is not perfectly representative, it is real. And it is now approximately 22 billion kilometers from Earth, attached to a spacecraft that has visited 4 planets and crossed into interstellar space, moving at 15 kilometers per second through the thin plasma of the local interstellar medium in the direction of the constellation Telescopium. Whatever finds it, if anything ever does, will have found evidence that on a rocky world orbiting a mid-sized star in the Orion arm of the Milky Way, something existed that was curious enough to send a message into the dark on the assumption that other curious things might exist in the dark to receive it. The assumption may be wrong, probably is, on the specific scale of this specific record and this specific spacecraft. But the assumption is also what led to every scientific discovery in human history. The assumption that the universe is understandable, that its patterns are detectable, that something in the dark is worth pointing instruments at. The curiosity that made the Grand Tour possible is the same curiosity that made the Golden Record worth including. Both fit on the same spacecraft. Both are heading in the same direction. Voyager 2 launched 47 years ago. It has passed Jupiter, Saturn, Uranus, and Neptune. It has crossed the heliopause. It is now in interstellar space, and it is still going. The journey does not end with the loss of signal. The trajectory continues, the record travels. The questions Voyager 2 asked at 4 planetary systems continue to be worked on by researchers who were not born when the spacecraft launched. The mission is not over. It has simply reached the phase where we follow the trajectory with mathematics rather than instruments. And that, too, is a form of knowing. It is, in fact, how all of this started. A graduate student calculating a trajectory, noticing a window in the geometry of the outer planets, and realizing what it meant. The window opened. Voyager 2 flew through it. And everything it passed is still there, waiting for the next machine to arrive and ask the next question. Neptune's atmosphere holds one more detail worth dwelling on before we leave it behind, because it connects the planet's wind speeds to a broader question about what drives atmospheric dynamics in the outer solar system. The question is, where does the energy come from? Jupiter's atmosphere is energetic. Its great red spot has persisted for centuries. Its jets and bands span the full circumference of the planet. The energy driving this activity comes from 2 sources: solar heating and internal heat. Jupiter radiates roughly 1.7 times the energy it receives from the Sun, meaning its internal heat source contributes substantially to the dynamics. Saturn's atmosphere is similarly energetic. Saturn also has an internal heat source, radiating about 1.8 times the solar input. Uranus's atmosphere is not particularly energetic, at least as visible in the cloud tops. The atmosphere is relatively featureless, and Uranus radiates essentially no detectable internal heat. The atmosphere runs almost entirely on the tiny amount of solar energy it receives. Neptune, at essentially the same distance from the Sun and the same approximate composition and size as Uranus, has an atmosphere with winds 7 times faster than any on Earth and storm systems as large as Earth itself. This despite receiving only about 0.1% of the solar flux that Earth receives. If solar heating were the only energy source, the atmospheric dynamics would be expected to be comparable to Uranus's quiet disk. Instead, Neptune radiates 2.6 times the solar energy it receives. The internal heat dominates, and that internal heat drives one of the most dramatic atmospheric systems in the solar system. The mystery is why Uranus lacks the internal heat that Neptune has. They formed in roughly the same region of the solar nebula, from roughly the same material, at roughly the same time. The models of ice giant formation that work for Neptune do not straightforwardly explain why Uranus retained so little heat. One hypothesis involves the formation history. Perhaps Uranus was struck by a large impactor that, in addition to tipping it on its side, mixed the interior in a way that suppressed efficient heat transport. The convection that carries heat from the deep interior to the outer atmosphere may be interrupted in Uranus by a layer of material at an intermediate depth that acts as an insulating barrier. Another hypothesis involves the composition. If the distribution of water, ammonia, and methane in Uranus's interior is different from Neptune's in the right way, the thermal conductivity and the ability to convect could differ substantially between the two planets. Neither hypothesis is confirmed because neither planet has been visited by an orbiter carrying the instruments needed to probe the interior structure. The only data we have from either planet's interior structure is the gravitational harmonics, the way the planet's gravity fields deviate from that of a perfect sphere, which constrains but does not determine the interior density distribution. Resolving this question requires either a Uranus orbiter, a Neptune orbiter, or ideally both. The Decadal Survey chose Uranus because a mission to Uranus is achievable using existing launch vehicles and gravity assist trajectories in the near term, while a mission to Neptune faces more challenging trajectory options. But the scientific questions at both planets are deep and connected. The termination shock, the boundary where the solar wind slows from supersonic to subsonic as it encounters the back pressure of the interstellar medium, is a final environment that Voyager 2 passed through on its way out. It crossed the termination shock in approximately 2007, at a distance of roughly 84 astronomical units from the Sun. The termination shock is not a feature of any planet's atmosphere. It is a feature of the solar system as a whole, the boundary that marks the region where the solar wind's ram pressure is balanced by the interstellar medium's pressure. It is the heliosphere's equivalent of the boundary layer around an aircraft wing, the region where the flow transitions from ordered to turbulent as the two regimes meet. Voyager 2's instruments measured the magnetic field and particle density on both sides of the termination shock, providing the first in situ measurements of this region. The termination shock had been predicted theoretically for decades. Voyager 2's crossing confirmed the predictions and provided details that constrained models of the heliospheric structure. Beyond the termination shock in the heliosheath, the solar wind continues its outward journey, but at reduced speed and with turbulent, disordered flow. Voyager 2 spent approximately 11 years in the heliosheath before crossing the heliopause in 2018. 11 years of measurements of a region of the solar system that no spacecraft had ever sampled before, in a direction that Voyager 1's trajectory had not covered. The heliosheath is not empty. It is the zone where the solar and interstellar environments interact, where magnetic field lines from both regimes are tangled and reconnected, where energetic particles from both the solar wind and the interstellar medium are processed and modified. Understanding it is essential for understanding how the solar system interacts with its galactic neighborhood. Everything Voyager 2 has passed, from Jupiter's volcanic moon to the boundaries of the heliosphere to the interstellar medium itself, is part of one continuous trajectory, one unbroken line from a launch pad in Florida to a point in space that no human will visit for tens of thousands of years. The line is still being drawn. It passes through everything worth knowing about in the outer solar system, and it ends somewhere in the interstellar dark, still moving, still transmitting while the power lasts, carrying its record and its questions and the memory of 4 worlds that no other machine has visited before or since. This is the mission. 47 years of it, and counting. There is a specific way that the Voyager 2 mission illuminates the gap between what we know and what we could know, and it is worth naming explicitly before the final close. We currently know, from spacecraft observations, a substantial amount about the inner solar system and the gas giants. Mars has been visited by dozens of orbiters and landers. Jupiter and Saturn have had dedicated orbiting missions, Galileo and Cassini respectively, that spent years in each system and provided data sets that continue to generate scientific publications decades later. Even Pluto, the small, distant world at the edge of the Kuiper Belt, received a dedicated flyby from New Horizons in 2015 that transformed it from a blurry telescopic point into a world with mountains and plains and a heart-shaped nitrogen ice sheet. Uranus and Neptune have not. The only close-range data from both planets comes from Voyager 2's flybys in 1986 and 1989. Everything else we know about them comes from telescopes, Earth-based and space-based, that can resolve them as small disks but cannot see their surfaces, probe their atmospheres, or characterize their moons in any detail. This means that 2 of the 8 planets in our solar system are known only from a single flyby, 35 to 40 years ago, supplemented by telescope observations that cannot tell us most of the things we would most want to know. For comparison, imagine if everything we knew about Mars came from a single Mariner flyby in 1965, supplemented by telescope observations. We would know Mars has a thin atmosphere and polar caps and some features. We would not know about the Olympus Mons volcano, or the Valles Marineris canyon system, or the evidence of ancient riverbeds, or the composition of the Martian soil, or the evidence for past habitability that multiple Mars missions have found over decades. Our knowledge of Uranus and Neptune is at approximately the level of our 1965 knowledge of Mars, a blurry first look that showed something interesting and raised questions that have been waiting for follow-up ever since. The follow-up to Mars came because the scientific community recognized that the questions raised by the first look were important and worth answering, and because the political and funding environment for planetary exploration was favorable enough to fund the missions required. The follow-up to Uranus and Neptune has not come yet. The Decadal survey has recommended it. The scientific case is strong. The funding has not materialized. Voyager 2 showed us that the ice giants are extraordinary. It asked a dozen questions for every one it answered. It revealed worlds stranger and more complex than any prior model had predicted. Those questions are still waiting. Somewhere in the outer solar system, Uranus continues its slow-rolling orbit, tilted on its side, with its strange offset magnetic field and its moon Miranda and its 10-kilometer cliff and its featureless disk that hides an interior we do not understand. And Neptune continues its faster orbit, with its incredible winds and its captured moons spiraling inward toward eventual destruction, its geysers still erupting from Triton's surface, its great dark spot replaced by new spots that form and dissipate on timescales of years. Voyager 2 passed both of them. It is now in interstellar space. It will not answer the remaining questions. That is our work. And the work is waiting. Strap in, keep looking outward, and stay with the crew. If you want more mission briefings like this, subscribe for the next journey.